Hey, Algebra 2. Today we are going to do exponential growth and decay word problems. Now to do these, you're going to want your note sheet because these problems are on there, and then you can walk through them on there. So you're going to need your note sheet and your calculator. Okay, first thing is we have three sets of formulas that we're going to use. One deals specifically with growth and decay. One is a compound interest formula, and one is a continuously compounded interest formula. So the first thing you want to do in any of these problems is to figure out which formula it is that you're going to use, and the words on the problem will help you decide which one it is that you're using. Okay, so first one here. In 1980, 2,180,000 workers worked at home. Over the next 10 years, this number increased by 5%. Write a model for the number of workers W in millions T years after 1980. Okay, so what symbols are we using here? We are using W to represent the number of workers, and we are using T for the number of years after 1980. Okay, so we need to write a model, and what we're going to do, because this talks about increase, this is an exponential growth problem. So we're going to use this first formula here. Okay, so this is what we use when a quantity is increased or decreased by a fixed rate over a period of time. So that should sound familiar with what I just read. Okay, A is the initial amount. So the initial amount is 2,180,000. However, we are supposed to have W to equal the number of workers in millions. So in millions, this is 2.18 million. 2,000,000.18. Okay, so our A is 2.18. So A is 2.18 million. And then what is the growth rate? If it's growth, it's positive. If it's decay, it's negative. So we're going to have a growth rate of 5%. So R is equal to 0.05. T is our time period. T is our number of years after 1980. That's the number we don't know. And then Y is our final amount. And so Y is going to be our W. That's our model for the number of workers. That's our final amount of number of workers. So W workers. Okay, so if we plug it into our formula, we have W equals 2.18, 1 plus 0.05 to the T. So essentially this is taking 2.18 million and adding 5% per year. Okay, so let the formula make sense for you. So to get the total number of workers, we're going to do 2.18 million times an increase of 5% for each year, and T is the number of years. Okay, so this is the model. This is what we call a model. There's no answer here. This is what we can use to find a whole bunch of answers. So now you're supposed to graph this in your calculator. So pull up your calculator and go to Y equals, and in Y equals, clear out whatever's in there, and we're going to type 2.18 parentheses, and you can type in 1 plus 0.05, or you should know that that's 1.05 to the, and since we don't have a T button, we're going to use our X, and then we're going to graph it. Okay, so there is an exponential growth model, but it doesn't really look like it. It kind of looks like a line, and that's because of where we're zoomed. So we're going to go to zoom, and we're going to use a new function here. We're going to go to zoom fit. So scroll down to 0, and 0 is zoom fit, and press enter, and it should fit the graph into a screen where we can see that it's actually exponential growth. So there's our graph, and we can see what it looks like. Okay, let's go move on to these all say part A. Obviously this is B and this is C. So part C, use this model to predict when the number of workers will reach 3.22 million. So I need to know when W is 3.22. And in our graph, this is Y. So where on our graph is W equal to 3.22? So what I can do, if I know Y and I need X, one thing I can do is just trace around. So I need a Y of 3.22. I can just keep going to the right. And I can find 3.23. That's pretty close, and that's after about an X of 8. So we're just going to make a rough guess here that that's going to be about when X equals 8. Okay, and remember we put in X, or we put in X for our T, so this is T. And that represents, T is the number of years after 1980. So what year is this? This is in 1988. Okay, next problem. Here we're going to use two different formulas to do compound interest. And either we're going to compound a specific number of times per year. Okay, so this is when we have a specific number of times per year. And this is when we compound continuously. Okay, so this is the difference in the two formulas, is whether we have a specific number of times per year or continuously. And what compounded just means is how often the interest is paid. Is it once a year, twice a year, once a month, which would be 12 times a year, or continuously? It's just continually putting interest on top of your interest. So we're going to deposit $1,500 into an account that pays 6.5% annual interest. Find the balance after 3 years if the interest is compounded annually, semi-annually, quarterly, or continuously. Okay, so the first thing we're going to do is look at these formulas, and you'll notice they both have an A. That is your final amount. So that's almost always what we're solving for. So we are looking for A. That is our final amount. Then they both have a P. That is your principal amount. That is how much you start with. P is your principal amount. That's how much you start with. So in this case, we start with $1,500. R is your rate. R is your interest rate, which you always write as a decimal. Okay, so 6.5%, 6.5%. Move the decimal 2 to the left, or you know that 6% is 0.06, so this is 0.065. Be careful you don't write this as 0.65. That would be 65%, and that would be a whole lot more interest. Okay, so annually, this is where it's going to change. Annually here, N is the number of times it's compounded a year, and annually means every year. So this is one time per year. Semi-annually, like a semicircle is half a circle, so semi-annually is every half of a year. And how many times a year would that be? That would be 2 times per year. Quarterly, think if something is broken into quarters, basketball game is broken into quarters, okay, 4 quarters in a dollar, so quarterly means 4 times per year. And then continuously, this is going to be the other formula. So this is where we know we're going to use this formula here. The first 3 are all going to use this formula because we have a specific N. Okay, so now we're just going to plug into the formula and make sure that we're good at putting it in our calculator. Calculator is huge. If you didn't get your calculator on the last problem, get it now. These are tricky to put in. All right, so we have A equals P, which is 1,500, times 1 plus, and here we have R over N. So 0.065 divided by on A, this N is going to be 1, to the NT power. So to the 1 times T power. Oh, we forgot to say what T was. We know what T is here. What is T? T is how many years we are doing our money here. How many years are we putting? And our T is 3, so this is 3 years. So that's what goes there, is N times T, which is 3 years. All right, so let's put this in our calculator and see how much money we would make if this was the account we were using. Whoa. Okay, so what we're going to do is we're going to clear this. So we're going to quit out of here, and we are going to enter this in. So we're going to do 1,500 parentheses 1 plus, and now we don't really need to divide by 1. We know that 0.065 divided by 1 is just 0.065, so we're going to do that step in our head. And we also know that 1 times 3 is 3. So I'm not going to type in 1 times 3. I just know that this is going to be to the third power. Press enter, and we get $1,811.92. So $1,811.92. Where should you round when you're talking about money? Well, you should round just like this, because that's how we talk about money. Okay, so now I'm going to switch up colors here, and we are going to do n equals 2. Okay, so for n equals 2, that changes our formula. So we have a equals 1,500 times 1 plus, it's r over n, so 0.065 divided by 2 to the nt, so to the 2 times 3. So we're going to pull our calculator back up again, and we're going to enter this in now. Okay, so we're going to do 1,500 parentheses 1 plus. Now we need to do the dividing by 2, unless you know that in your head. So 0.065 divided by 2, end parentheses, to the, and I'm sure you know 2 times 3 is 6. So type in 6, we press enter. Well, now we're going to make a little bit more money because our interest was given to us more often. Okay, so interest was given to us twice a year instead of just once. So we've got $1,817.32. Okay, so there's our answer for semi-annually. Now let's move on to quarterly. Okay, so quarterly is 4 times a year. So we're going to plug in n equals 4. So we have a equals 1,500 times 1 plus r, which is 0.065, over n, which is 4, to the nt, to the 4 times 3. Okay, so again, we're going to enter that in the calculator, but I'm going to do a little trick here, and I'm going to press second enter. What pressing second enter does is pulls that equation back up, and I'm going to go over, and I'm only changing this 2 on the bottom to a 4, and this 6 up here to a 4 times 3, which is 12. So instead of retyping it in, I can just go ahead and do that, and I get $1,820.11. Okay, last one. This one's continuously, so this one is a little bit different. It's a different formula. So how do we compound continuously? We use what we fondly refer to as the PERT formula. A equals P times e to the RT. Remember, E is that number that's 2.1828, so on. So we're just going to plug in A equals 1,500 times E to the R, which is 0.065, times T, which is 3. And that's now what we're going to type in our calculator. So we're going to pull up our calculator, and we're going to type in 1,500 times E, which is second ln, and that automatically gives you the exponent. And now we need to be really careful, and we want to put our exponent in parentheses here. So we're going to do 0.065 times 3 in parentheses, so that that whole thing is our exponent. Enter, and we get $1,822.97. And what was it? 97 cents. And there you have it. Here's the next slide. Pause right here before I run out of time and complete this for class tomorrow. Have a great day.